This talk is about communicating underwater by playing sound on light. The oceans around us hides amazing life forms, lost cities, ancient shipwrecks preserving life, culture, and architectural marvels. Imagine digitally mapping these submerged cities. To do that, we can send a remote asset, equip it with a camera, and capture images. But we surface dwellers do not live in water. The best we can do is live on a ship or a base station. Then, how to get these images to us? Obviously, traveling back is not an efficient solution. Can we use tethered links? Yes, but often these are very restrictive in nature. What about wireless technologies? Say if we had air instead of water, we have a whole set of technologies to serve us, like Wi Fi, Bluetooth, etc. But underwater, these technologies are of no help. This is because radio waves attenuate underwater, making these technologies useless. In fact, it is easier to transmit information in outer space than underwater. Then the question still remains, how do we map these interesting underwater worlds? One of the earlier attempts suggested to encode these images into bits and then encode these bits into sound signals and transmit the sound to the base station. You know what was the speed they were able to achieve with this? 1 kilobits per second. And the best they were able to do was send text messages. A natural question is, can't we just increase the frequency of sound to achieve higher speeds? That can't be done because high frequency sound attenuates with distance and die before reaching the base station. Another solution to mitigate distance problem was to use light instead of sound, something like a pulse laser to send bits, 1 with laser on and 0 with laser off. While the solution is good, these pulse lasers consume a lot of energy. The question is how to achieve high speeds but low energy consuming underwater communication. To answer this, let's say if we place the pulse laser at the base station instead of the remote asset, like this, and then equip the remote asset with an inexpensive corner mirror. Corner mirrors are great for sending the light back in the same direction, establishing reverse link made of light. This send back light is called backscattered light. With this, we have established a link, but to put information on this link, we need some devices at the remote asset. Prior art has used mechanical devices limiting their speeds to tens of kilobits per second. The obvious question is how to speed it up. To answer this question, let's recap about sound. High frequency sound dies with distance. For shorter distances, high frequency sound is still a viable solution. Okay, but how does it help? Let us see how it does. Earlier, we were playing the sound towards the base station. Instead, if we play the sound on the backscattered beam, maybe we can put information on the backscattered beam, whereby we are using backscattered light and sound together, making it acousto-optic backscatter communication. And as the distance between backscattered light and the speaker is short, we can still use high-frequency sound signals which does not have mechanical inertia. Let us see how this technique puts information on the light. Consider a block of water as shown here. When we play sound in water, pressure changes and introduces compressions and rarefactions. The change in pressure also changes refractive index of water. Mathematically, sound, pressure, and refractive index change sinusoidally. In 1D, they look something like this. If no sound is played, light entering water medium propagates straight. But when sound is played, light won't go straight. Instead, it curves and focuses. Now, if we place a camera at a focus spot, we see a high intensity, and at a defocus spot, we see a low intensity. If we interpret focus as 1 and defocus as 0, we can use this physics phenomenon for communication. But this simple sound signal only puts 1 at a particular time and a 0 after an interval. And this is not useful information. It's alternating ones and zeros. Then how to send meaningful data? We have 5 signs here, which travel forward in time. If we modulate every sinusoid's phase, and pulse laser at the same frequency as sound, and phase modulation of the sound is based on the signal we want to send, which is 01101. So does the sound signal affect the light we see at the camera? Yes, it does. Initially, we see a rarefaction, making the light defocus, and the camera sees a low intensity, recording 0 to the memory. After a time period Ts, we have a high intensity, thereby adding 1 to the memory. Now observe the next time period very carefully. Earlier we saw a high. Now we are seeing another high due to the modulated sound signal, whereby sending 2 consecutive ones, allowing custom bit information to be sent. Then we see a 0, finally a 1, obtaining required data just by looking at light intensity. When this camera is present at base station and speaker at remote asset, we have a working communication system. To realize this phenomenon, we built a lab prototype. First, we have a base station and a remote asset. The base station has a laser and a camera. The light is directed towards the remote asset. The remote asset has a corner mirror to send back light, also a high frequency speaker. The speaker plays sound to focus light onto the camera as shown here. With that, we have a working laboratory prototype. Then the first thing we have to do is to evaluate this device under various harsh conditions in the lab, some of which are mentioned here. Before testing harsh conditions, we should know if the system can transmit images well. As digital cloning needs transmission of JPEG images, the transmission has to be accurate. The communications community uses a metric called as bit error rate to measure this accuracy. And the acceptable range is 10 power minus 3, which means for an image of 150 kilobytes, we can only afford 1200 bits of error. And the error rate we were able to maintain was 120 bits, maintaining a high PSNR without any error correction mechanism. Just to note, prior art was only able to send text messages, and we can send images and much more. With such low error rates and 100 times increased speeds, we still consume similar amounts of energy compared to state of the art. The next obvious check is to know how much distance can we do this for. To check this, we folded light paths between mirrors, increasing the transmission distance. And with the folded paths, we observed error rates between 10 power minus 5 to 10 power minus 4. Along with the distance, error rates are also affected by the murkiness of water. To test this, we took clear water and started adding milk powder to it, making it murky as shown in the right. As the graph shows, error rates increase as the amount of milk powder gets added. This is obvious because the received light intensity at the camera reduces as shown in the right. But it also gives us more information. Say if we use Beer-Lambert's law and plug in attenuation coefficients of clear waters and coastal waters, we can reinterpret earlier data and get equivalent clear water distances as shown in the left and coastal water distances as shown in the right. And we theoretically can hypothesize our prototype can function at distances marked in the graph. Another factor that affects optical transmission is turbulent waters. To test this, we introduced a rotating wheel inside the water, making the water turbulent. Even then, we observed stable transmissions as shown in the inset here. With these experiments, we wanted to test if the method can scale with a higher frequency speaker. So we replaced 5 times higher frequency speaker than the previous. When we transmitted data, we observed negligible error rates, confirming the scalability of the system. Now that we have tested our prototype extensively, can we deploy it and use it for digital cloning? Unfortunately not. While our laboratory experiments show promising results by harnessing power of sound and light, the real water tests were not very successful. One of the reasons is the apparatus we had was very bulky and was unable to maintain stability against surface waves. Miniaturizing the setup will improve the stability from these waves. Another limitation is we repeat the bits for better transmission, which also affects the speeds. Coming up with better ways to modulate sound would be a great idea. With that, I conclude my talk. Please visit our poster with questions. This is our website link.